general equations. So what this means is that I like to think about algebraic varieties, which are the solution of polynomial systems of equations. And in algebraic geometry, this is the main object that is studied in general. So that is why algebraic geometry will have a play in everything that I will tell you about. But if you don't know what an algebraic variety is, not to worry. I will try to just give you an intuition of what's going on. Okay. Right. So this application that I'm going to show you is related to computer vision and is the structure from motion problem. So in this problem, what happens is that we have a bunch of pictures of an object or a scene, and our goal is to create a 3D model of what appears in the picture. And a 3D model has two components. One is the position of the cameras, and the second component is the actual object. Okay? So at the end, a 3D model is going to look something like this, right? So you're going to have, let's say, all of these pyramids are just the camera position, so the camera that took the pictures, and then you're going to have either a point cloud or a line cloud, let's say, that when you look at it, is going to resemble the object that was in the images, okay? And something that is important, I'm talking about the position of the cameras, and I'm referring to the relative position of the cameras, right? So it's just how the cameras are located with respect to each other. So how do we do this? There is a pipeline, this is like a general pipeline that has 4 steps. So the first step is, of course, data collection and feature detection. So in feature detection, what you do is that you want to find relevant, significant features of the things that appear in the picture, right? So normally, this means that you're gonna identify significant points or lines. So if you reconstructed this beautiful room, maybe you want to identify the corners of the table, those are your points, and the lines are gonna be, let's say, the actual corners and so on. That is what you want to do. Oh, sorry. Then, once you have done that in each picture, what we want to do is to pair them according to potentially coming from the same 3D object, right? So you want to say this point and this point are the image of the same 3D point, right? And the same with lines. That is the matching process. Once you have done that, you forget about the pictures. And you are left with tuples of points and lines, and you do camera pose estimation and triangulation. So you use this geometric data to estimate the position of the cameras and then decide where this point tuple that you saw, right? Where is the 3D point that generated? That is what you want. And finally, if you have like a big scene, then what you do is you patch that together around all the objects, and then you get your 3D model, okay? That is the general thing. So my research has been done mostly on this part, on the triangulation part, because that is where you have, the starting point of that process is geometric data, right? So that is when you say, oh, I can maybe say something about this with algebraic geometry. However, I'm gonna, since I know that we have very different backgrounds here, I am gonna spend some time in the first 2 parts. I'm just gonna briefly mention a couple of results where actually deep learning has helped to refine the data that we get, so we can do better camera pose and triangulation, and then I'll tell you about the main part of my research. So feature detection, normally when it's done like by hand, let's say, is done by dividing the image in different pieces, and then you try to identify these points and lines locally by maybe identifying change of colors in the pixels or something like this. However, what happens in that case is that the feature detection is very sensitive to environmental factors in the image, right? So for example, if you have a picture of a church, right, it's gonna look very different if the day is cloudy or if there is fog, right? Like it's gonna be problematic. So what happens is that actually using deep learning, you can actually refine the data, right? There is also something that happens, and is that if you have, let's say that you have this table, and you have a certain light, where you get light from here to here, and then you get a shadow from here to there, then what happens is that maybe you are actually identifying this point as a critical point. And you don't want that because this is not a corner, right? So using deep learning, you can actually learn whether this point is relevant or not. Or you can distinguish, for example, different lines, like pattern lines and decoration lines, from structural lines. So this is something where deep learning has actually helped a lot. There is a lot of literature about it. I don't think you can, it's very possible to see it here, but this is just an example of one of the papers that where they use deep learning to refine the data that they get. And what happens is that this is a handcrafted method. And you see here that there is a bunch of noise and significant points in this chair that are identified. And when you use deep learning, which is this row here, then you actually get way less, and the ones that are more significant. And this is the ground truth. So this is the original database, which is very similar to the deep learning one, right? So there is a lot of literature about this, a lot of works, a lot of benchmarking. There's a lot of things going on there. So once you have your data, remember that I told you about matching. Again, there's a lot of literature about it. And when it comes to deep learning, again, the main contribution that has been done is refining the matching of pattern lines, right? So as I was saying, you can learn whether like a pattern line, a decoration line like this one here is important or not, but you can also decide better whether you want to match this line in one picture to another one, right? So that is some of the refinement. This is implemented in some software. And what has been done with that is that, again, we get a better quality of data. We get some data that is maybe more meaningful. So now what do we do with the data? So again, remember that at this step, once we have the data, we forget about the pictures. So we just have points and lines, okay? And this is where algebraic geometry comes into play. And the first thing that I want to do is to explain how do we model these data, these points and these point tuples and line tuples that we get? How do we model that using algebraic geometry, right? So the first thing that we do is that we want to say what it means to take a picture. What is the meaning of taking a picture, right? So the meaning of taking a picture is just applying a function. It's just going to be applying a function. And this function is defined over a set x, and a set cm goes to a different set y. And this set x is going to be all the features that I see, right? So if I can identify points, then this x is going to contain points. If I have points and lines, then this set is going to change. This cm is going to be the set of cameras. So if I have n pictures, then the elements of this set are going to be tuples of n cameras, right? And finally, this set y is just the image of the features that appear in x via the cameras that are in cm, right? This is a very abstract definition. And of course, the set x can change a lot. The set cm is going to depend on the camera model that we choose. And just as an example, if in our data we have 5 points that we observe with 2 cameras, right? So we identify, we have 5 tuples of 2, okay? That is our data of 2 points. Then the function that we are modeling is a function that goes from points in 3-dimensional space, but we have 5 points, so we have p3 to the 5, times c2 because we have 2 cameras. And then the image is going to be 5 points in the first image, which is a 2-dimensional space, times the 5 points in the other images, which is another 2-dimensional space, right? However, if I just observe one line, if my data is just a tuple of one line, my function is going to go from, my function is going to go from this set is called the Grassmannian of lines in P3, right? The Grassmannian of lines, if you don't remember what that is just the set of lines in three-dimensional space, but it's just projective space, so we are not thinking about the origin, and they all intersect, even if it's at some point in infinity. Just a set of lights in between. And then, again, we have two cameras, so the image space is just the Grassmannian of lights in the first image times the Grassmannian of lights in the second image, okay? So, again, the definition of this function depends on the data that we have, but this is the general model. And now, I haven't mentioned what the cameras are. And this depends, of course, on the data as well, right? So there are many different types of cameras. So, for example, pinhole cameras are cameras that, when you take the picture, all the scene is pictured at the same time. But rolling shutter cameras are, they work, they scan the image, right? So they don't take they don't picture the whole scene at the same time, they just scan the image. So if you have movement, for example, if you're taking the picture of a fan, with a pinhole camera, you're gonna see the blades of the fan just fine. But if you have a rolling shutter camera, then you're not, because you are just taking the picture one line at a time, and then the blades are moving, so you're not gonna be picturing that. This is a nice picture, but this happens also when you're trying to take a picture like from the train, from a bus, using your cell phone, because normally cell phones have rolling shutter cameras, and then the house looks like this. That's the reason, okay? And then there are other types of cameras that I think are fun, the fisheye cameras, because those are the ones that have the GoPro. So if you, if you put the camera in a certain angle, you might look really funny by, doing your activities. Anyway, those cameras are just fun. The work that I've done focuses on pinhole cameras. Mainly, one reason is because they are simple to model, but also because, for example, they are equivalent to rolling shutter cameras for static images. Okay? So if there is no movement, it really doesn't matter. So the pinhole camera is a good model for both of these. So this is the main model that we will choose. And the way that we model this camera is just by matrix multiplication. It's just going to be a linear projection. Okay, so a pinhole camera is just going to be a 3x4 full rank matrix that that takes a point in space and then sends it to just the product of the matrix by default. It's very simple, just a linear projection. However, this function is not going to be defined in one point, which is the kernel of the matrix, right? And the intuition, I'm going to call it, normally if I have an uppercase C for the camera, its kernel is going to be lowercase c. And the idea, the intuition behind this point is that this is where the camera is located, because the camera cannot take a picture of itself. Okay, so that is the idea. Right. So that is what a camera is. So now our map, the map that I had before, my set X is still going to change, but now I'm going to think of the CM as a tuples of matrices. Okay. So now, sorry, let me go back for a moment here. So what does it mean to reconstruct, to do some reconstruction? It means that I take a tuple of this set Y and I want to find the pre-image of that point via this function. So in algebraic geometry, this just means that I'm computing the fibers of this map, right? So what can I say about the fibers? So since our sets are changing quite a lot depending on the data, the first thing that I want to do is say something about when can I actually compute the fibers, right? Because if the sets change so much, then maybe I compute this pre-image and I have a finite set in the pre-image, or maybe I have infinite sets, it's an infinite set, or maybe I don't have any pre-image at all, and it's gonna depend on the data. So this is solving this question related to solving something called minimal problems, which means that I want to find a minimal problem is just a setting, a set of data and cameras where the joint camera map has generically finite, not empty fibers. Yeah.
So I just wanted to understand the problem setup. Sorry. So you define the points to be in Pn because this is in relation to the camera, which is located at the origin, right?
The points, They're in P3, not just
Sorry,
in space.
P3.
Yeah. Yes, exactly, because we want to find them their position related to depending on the camera and not to the origin.
So how does this work if you have multiple cameras? Are they like located in different locations? And if so, how do you define this relation?
You want the relative position of the cameras as well.
Okay.
So what you end up computing is if you have a camera, then you compute the relative position of the next one and the relative position of the point with respect to those cameras.
Okay.
So technically you could rotate the whole scene and it shouldn't matter, right? So that's why you use this relative
Okay, that makes
relative
sense.
positions. Yeah. Right, so a minimal problem is a setup where this map has generically finite non-empty fibers. Okay? So what I'm going to show you two examples of problems that are not minimal, so we understand what being minimal is. So the first problem is I'm just observing one point with one camera, right? So observing one point with one camera means that my map goes from P3 times matrices of size 3 by 4, just one matrix, right? And it lands in P2. So I'm supposed to compute the pre-image of this map. So, but if we think about the geometric intuition, what is happening is that I am observing one point in the camera and I want to compute its pre-image. But if I only observe one, then I have infinitely many possible pre-images, right? Which are all the points in this line. So it's not a minimal problem because when I compute the fibers, that fiber is infinite, okay? And here, the second one is I observe one point with two cameras. So that means that I observe, let's say, 2 points, right? And if I want to find the pre-image of this sample, this means that I have to find one point in space, such that when I take the picture with the two cameras, then I am going to get these 2 points, right? That means that the pre-images of the 2 points these 2 lines have to intersect in free space, right? And sometimes this happens, but generically it doesn't, right? So in this case, the problem is not necessarily that the fibers are not finite, but it's just that they are generically empty, okay? So a minimal problem is a balance between the amount of data and if I can do the reconstruction. In a paper that classified minimal problems, there was a paper by Timothy Duff, Kathleen Cohn, Anton Leikin, and Thomas Pajla. What they did was that they gave conditions on the amount of data and the cameras to have minimal problems, and they classified them, okay? Under the assumption of complete visibility. So that means that all your cameras see all your data, which is not always the case, but you can just split your real cameras in cameras that satisfy this condition. And they gave like a full list of minimal problems. So I know that maybe the list can be a little bit confusing, but for example, if we look at just at this part here, what this means is that a problem where I observe 5 points in 2 cameras is minimal. This Y is from my yes, minimal. And the size of the fiber is 20, right? So if I observe 5 generic points with 2 cameras and I try to reconstruct them, I'm gonna have generically 20 possible solutions. Okay? And this is the same with all the columns that appear here, with all the sections. So if I observe with 3 cameras, I observe 3 points and 2 lines that are adjacent to each one of the points, then yes, it's minimal, but now my fibers have 3012 elements. Okay? So I know that there are a lot of elements, but they are finite, so that means that we can use them to try to see if those cameras fit the rest of the points using Ransack. Okay, so you have finitely many options for the cameras. Okay, and this is good. So from this, once you have these finitely many points, you can see which type of cameras fit better, and then the way to do this, as I was mentioning, is just by solving, by doing some Ransack with the rest of the data. And I'm just gonna mention this paper. It's a paper by Peter Hubry and Timothy Duff again, and Anton Leikin and Thomas Pajla, a lot of the same people as before that appeared before. where they actually try to use deep learning to find a good point of initialization for ransom. Okay, this paper was presented, I think, in ICCB a couple of years ago, and it was like best paper. It was great because it was a merge of algebraic geometry, but also deep learning to solve these minimal problems, which is actually important. So it was a very good paper.
The second, what is ransom?
RANSAC stands for random sample consensus. So what happens is that, let's say you have a bunch of points that you have observed, and you identify these 5 generic points into cameras, and you have finitely many options. So what you do is that from those possible cameras, you try to see which ones give you a better approximation of the rest of the points that you observe in the image, and that is the camera position that you choose. So when they say random sample consensus, it's like we are just gonna try to fit the rest of the points as best as we can with the cameras that we chose at the beginning using these 5 points. Right. So what we get from this is the camera positions, and now what we have to do is to actually do the triangulation, right? So what we have to do is find an estimation of the point in space whose image was the tuple that we started with, right? Assuming that we already have the cameras that we got from the previous step. And the way that we do that is that we want to model like perfect points, perfect tuples, using algebraic varieties, okay? So what will happen is that I will have a set that can be described by polynomial equations, right? And that set is gonna be my model. So all the noisy data can be corrected to that model and then triangulated using computing the fibers. So how do we do that? Well, we define the varieties, and these varieties are they are called multi-view varieties, and then before you point, you write a point or a line depending on which data you have. But the point multi-view variety is gonna be defined by this. So you're gonna have the function that we had before, but you're gonna restrict it to just one camera tuple because we found the cameras before. So now our function goes from P3, from space, to P2 to the M, and I'm gonna see how the image of a point looks like through that tuple of cameras, right? So what this map is representing is all the possible tuples that I can get with that tuple of cameras, with those cameras. Okay. And the formal definition is that you have this map, and the point multi-view variety is the Zariski closure of the image of that map. Okay. Everyone remembers what Zariski closure means? No. Zariski closure is just the smallest set that can be described by polynomial equations. So what I want to do, the problem with this is that when I just collect the points in the image, maybe that set cannot be described as the solution of polynomial equations, right? But I know that I can find a set that contains it that can be described by polynomial equations, okay? So what I want to do is find the smallest one of those sets, because I like to work with polynomial equations, so that's what I'm gonna do. No, that's how I like it just because I like it. It's just because there's a lot of algorithms to optimize to polynomial models. So it's not just that I woke up one day and wanted to do this. Right. So this is just the smallest algebraic set that models perfect correspondences of image points, of tuples. And this variety has been studied a lot, right? So what this means is that there is a lot of polynomials. There has been a lot of work finding the polynomials that define this set. Also, the singular locus and the Euclidean distance degree, everything is known. If you don't know what this means, yes, no worries. It's just that this variety has been studied a lot, right? In particular, one result is this. So you can find the equations of this variety by building this matrix. So you have your n cameras, you're gonna stack them on a column here, and then you're gonna, let's say, write this u1 to un as variables. You build this matrix, and then you say that, and then the result is that a tuple of points is in the multivariability if when you replace this u1, u2 to un with the points, you get a matrix that is rank efficient. Okay? That is one of the results. So that is very nice, because what happens is that I can decide if a matrix is rank efficient by computing determinants. If I just compute the determinant of the matrix or the maximal minors of the matrix, because the matrix can be rectangular in this case. So if I compute the maximal minors of the matrix, those are polynomials, and I evaluate those polynomials in my data, and they vanish, then I have a correspondence. And if they don't vanish, then I don't. Good, we can decide, right? This is precisely what says here. And intuitively, what is happening is that these equations are telling me when the pre-images of the tuples intersect in a point. So what happens is, if I have this tuple of grid points, and I want to know if they are a correspondence, then I can check the determinants, but what is happening is that I'm taking all the pre-images, and if the determinants vanish, then that means that all the pre-images actually intersect in a point. That is the geometric intuition. Okay? Yeah.
Can the pre-images intersect in the line?
Yes. Yes, they can. So the thing is that, yeah, that is the intuition. They can intersect in a line, and that corresponds to a singularity of the variety. Okay? So the thing is that if your cameras are not collinear, then they will never intersect in a line. Right? If your cameras are everywhere, the pre-images are not going to intersect in a line. But if you have collinear cameras, right? And let's say that the tuple that you're taking is the tuple whose points are the picture of the other cameras by the picture of each other's cameras, right? So this point E1 is the image of the cameras C2 and C3 in C1, right? And all the cameras are collinear. Then what happens is that when you do the pre-images, you do these lines, and they are going to intersect in one line. And it's a line that contains all the camera centers, right? What is the problem with that particular setting? The problem is that you have infinitely many possible pre-images, so you cannot do the reconstruction effectively. What you can say is that generically, this doesn't happen. So for random cameras, this is not going to happen, and for random tuples, this is not going to happen. Yeah. So this is in algebraic geometry. This means that generically, this behavior doesn't hold. But if for some reason you find yourself in this situation, then this tuple here is a singular point of the variety. So it's a point where you have to be careful, okay? Because you cannot do the reconstruction effectively. Yeah. Actually, this is something, this singularity that I'm mentioning here, it's similar to one particular thing of the slides that Guido had like 15 minutes ago, where we had this surface and we had this spike at the end, right? That spike was actually a singularity of one variety, of the variety that appeared there. And those are not problematic points, but special points where you have to be a little careful. Like the behavior is not going to be the same as in general, okay? So yeah, this was part also of the result. There you go. So now, since the point multivariety had been very well understood, what we decided to do was to understand the line multivariety, right? So there is some value to study lines, and it's, well, the first one is that in buildings and in urban scenes, a lot of lines appear because there's a lot of buildings, right? And the other thing is that when you identify lines, they are less prone to mismatch right? So it's harder to mismatch lines than to mismatch points earlier, right? But the thing is that this type of algebraic models were not understood for lines. So that's what we started to do. So what we did was that we defined the line multivariety in a very similar way as what they did in the point multivariety. So we just took our image that goes from the Grassmannian of lines in P3 to the Grassmannian of lines in P2 to the n, because we have n cameras, and then we just collect all the possible images of lines. And then we do the statistic closure, and that's the line multivariety. And let's think for a moment when this map is not defined, right? I told you that a camera was not defined in its kernel. It was this point, right, where the camera cannot take the picture because it cannot take the picture of itself. But if now I have a map that goes from lines, which lines do you think that I cannot take the picture of? If I know that my camera cannot take the picture of itself.
The ones that it's full here.
That's one of the lines where I cannot take a picture, but it's not the only line, because I cannot take the picture of any line that contains a camera center. Okay? Yeah? Because the camera is not defined at that point, so my line is gonna be like missing something. Right? So this is now our kernel is a little bit bigger, but it's fine. It's fine. We just need to take that into account. But that is where that is the line multivariety, and then we did a very similar work to the one that they had done before, in the sense that we wanted to find equations, we want to understand this variety, understand how big it was, how it behaved. So I'm just going to show you one of the results. So for showing you the results, I will just denote the image of a line by each camera, just by this lowercase l. This is just notation, so we don't have things that are big looking here. But this is our main result. So our main result is that the line multivariety is given by the tuples of lines, such that when you build this matrix that also depends on the make of the camera matrices, this matrix has rank smaller or equal than 2. Okay? So it's very similar to the result that we had before, right? Because the result that they had done was, we have this matrix, if this matrix is rank efficient, then your point correspondence is good. This is very similar because what we have is, you have a tuple of lines. If this matrix that you construct is based on these lines, is rank efficient, no, it has rank smaller or equal than 2, your line correspondence is good, okay? This means that the variety can be defined by the minors of this matrix. I will make a remark, and it's to say that these equations only work if and only if no 4 cameras are collinear. Okay, so for 4 collinear cameras, these equations are not enough, you need a little bit more. And also that this result has been proven before for 3 cameras only by Joe Killier in his PhD thesis. This was just a small piece of one of his theorems. So the 3 camera case had already been done, but now we have more cameras. We generalize it. Right, so what does this mean intuitively? It's exactly the same intuition as we had before. If I have a tuple of lines and I want to know if it's a good line correspondence that I can reconstruct, then what I do is that I take the pre-image of each line, right? So now my pre-image of this line is not going to be just another line, but it's going to be a plane, right? This plane contains all the lines that are going to be this picture, and I do the same for the other cameras, and if they intersect in one line, then that means that my camera, my tuple that I started with is good, and I can measure it, right? Now we go back to the question, can they intersect in a plane? Yes, they can. And again, that is a singular point of the variety. That doesn't happen all the time. It will only happen if the cameras are collinear, right? That is the only option. Because the plane will contain all the camera centers, so it has to be collinear. That is precisely what is happening here. If something that I will say is that if you are familiar, if you are familiar and remember what happened in your algebraic geometry course, if you didn't block that out because it was so horrible to carry it with you, then you will remember that when you have determinant varieties, the singular points are the points where the rank drops, right? If you are collecting all the matrices, let's say of rank 3, then the smooth points are the matrices where the rank is exactly 3, and the singular points are the points where the rank drops. That is for general matrices. So in this case, this result will not be surprising. I know that these are not general matrices, like let's say they depend on parameters, but this type of rank drop is not going to be a surprise. It's what you expect. Right. So now to finish, I will tell you about the last part of the work that we did, and is that we have this nice variety for points, we have this nice variety for lines, but the problem is that in reality we are not observing like full lines, right? We observe line segments. So what we are actually observing is a point and a line that goes through it, right? So we decided to take a shot at that scenario, also with algebraic methods. And what we did is that we defined anchored multivariaties, right? And what this means is that you are either taking a look at all the points that are in a line or the lines that go through a point, okay? And you define them just by restricting the previous multivariaties. I have here the formal definitions, but I know it's a little bit of notation, but what this means is that I'm looking at scenarios like this, right? I'm just anchoring either in a line or in a point. And what we did was that we tried to find the equations defining these varieties. And we proved that they were also determinants, plus some linear equations that look like this. So you have the determinants that we had before, plus some equations. So this is nice, some linear equations, sorry. So this is nice because we have these very nice polynomial equations that define the perfect correspondences. And we ran some experiments, some numerical experiments for this setting, just to try to compare it with previous methods to see if maybe anchoring these varieties was better. And it was. So that was nice. It was, the biggest difference was speed, because let's say that you have a line going through a point, right? If you don't take into account the point, then you have to minimize, you have to correct your data, let's say, with respect to all lines to find this one, right? But if you take into account the fact that it's going through a point, you only have to minimize your distance over the lines that go through a point. So you are like getting rid of a bunch of candidates that don't work. So the improvement in speed was, it was nice, but when you think about what's happening, it makes sense, because you are removing a bunch of data that is not going to work. And the accuracy was actually very comparable to like traditional methods. I have to say something, a disclaimer again here in this part, and is that normally these implementations are done, are thought as, algorithms that have to finish really, really, really quickly, because in practice you have like millions of points, and so you have to solve these minimal problems, and you have to do this triangulation really, really fast. And up to now, there are no solvers, there's no implementation for the anchored case, right? For this case. If anyone is interested in this and have the skills and like to code and is interested in this, please let me know, because I will be very interested in doing this. So this has not been done. So when we did this implementation, we compared it with implementations that were done in a very similar software to ours. Like, it was not the very specialized solver, because we didn't have a specialized solver either. So we knew that maybe in some cases we could not compete. So we have like similar implementations, but yeah, it makes sense. We're near the end. We are almost there. I show you 3 varieties, one for points, one for lines, one for the anchored case. I show you a little bit about the minimal problems. But what's left to do? Well, there's plenty of work, of course. But the first thing is, as I was saying, the implementation. The second thing is the error correction, right? I didn't mention any of this in this talk, but there are algebraic measures for the complexity of correcting the error to these varieties, right? Because you have your model that is this very nice thing described by polynomials, and when your data is noisy, you want to find the closest point, right? So how hard deciding how hard this is can be done using, can be estimated using some algebraic methods as well. We haven't done that, but that would be also a nice algebraic work. This part here is more theoretical. The first one is more practical, of course, the implementation. And this was just a very quick and short introduction to one of the problems that can be solved using algebraic geometry, but there's plenty more. And if you're interested in these type of things, there is this very nice survey called Snapshot of Algebraic Vision that was published in 2022. Maybe I'm wrong, maybe it was 2023. No, it was 2022. By Joaquin Lacatleman. And it's not a research article, it's a survey. But it contains computer vision problems from the algebraic perspective. Okay, so very nice. And there is also Joaquin's PhD thesis, algebraic geometry for computer vision, but it's like also a good starting point if you want. Now I think that's all. These are the QR codes for our two papers. And thank you for I don't know if you have any questions. If you don't, that's also okay. If you want to talk about this later, I'm also very happy to tell you more or to, hear your questions. Yes. Oh, sorry.
Is it possible for, like, in the point case, for perhaps the three pre-images to meet not in a point but aligned to a subset of points, like for just an interval, and then to diverge again?
No, that's when you have, in that case, there are some arguments where you can show that it's, because the intersection of two lines is always a point.
Yeah,
Right.
Can it be curved? Is that like the,
So your pre-images are always going to be, so if you take a point, the pre-image is always going to be a line, right? So you're going to have intersections of lines, and those are always going to be points. There is one work where instead of observing, like here we are dealing with images of points and images of lines, right? There is one work where they deal with images of curves.
Yeah.
So in that case, your pre-image is a cone, right? So it's, I don't know if I can show this, but I will give it a go. So let's say that you have your camera. You have your camera here, and what you observe is a curve like this. In that case, when you take the pre-image, what happens is that you get a cone, right? You get a cone that looks like this. It's a whole cone. And if you have two cameras, and you observe here like, I don't know, a little flower, right, for some reason, then your pre-image is gonna be, again, a cone that now looks like a flower, and your pre-image is gonna be just like the intersection curve of those two cones. And in that case, then weird things can happen, because maybe you can have like more than one connected component in the intersection. Like weird things can happen. And there is one work where they study some of these cases, but from the algebraic point of view, I think it will be a really fun problem to understand the intersection of these two cones and conditions for, understanding the dimension, the connected components. So it would be really fun.
Are these varieties related to like Schubert varieties?
They are very much, yes, they are lovely. And actually these points, for the line of the varieties, the kernel of each camera is a Schubert cell. And then they are actually also isomorphic to the blow up of the Grassmannian along the Schubert varieties. It's really nice. They're really beautiful. Yeah. And I just excited about this. There is also a very more recent paper, but there is a generalization of these varieties where they don't go from the Grassmannian of lines in P3, but from the Grassmannian of K-planes in PM to these other things. And then the sugar variety is a bit way more prominent there. But yeah. If there are no more questions,